Now let's consider strong acid and bases. This is the simplest case. There are a lot of, maybe innumerable acid and bases, but most of them are weak acid and bases. There are just a few strong acid and bases. So you simply memorize which which ones are strong acid and strong bases. Okay. Strong means the when it dissolved in water, it, it is completely dissociated. Okay. For example, this is a symbol of strong acid HX. Yeah? It dissociates into proton and an ion. Okay. In the meantime, strong base is represented as MOH. Again, when it dissolves in water, it dissociates into M plus and hydroxide ion. Okay, since strong acid produces protons, it is acid. In the meantime, a strong base, any base actually, produces hydroxide ion. Okay. Let me ask you a very simple question. What is the dissociation constant for this strong acid and strong base? Okay. Can we define the dissociation constant? Well, since there is no uh, HX form or MOH form left after dissociation, so the the denominator of the equilibrium constant is almost zero, so equilibrium constant is almost infinite, okay, very large, practically. So usually people uh, do not consider the actual value of dissociation constant of strong acid and bases. Simply we consider they are too large, okay, to be measured. Alright, but actually we can measure and then it has finite values. Alright, now let's consider this example. What is pH of 0.1 molar hydrobromic acid? Yeah? This is a strong acid. What's the pH? And we write this chemical reaction here. The hydrobromic acid, when dissolved in water, it produces hydrogen ion and bromide ion. Okay, the reaction goes to completion. Okay, there is virtually no reverse reaction. But to treat this uh, acid, we simply omit this water molecule here. So instead of writing this way, we simply write it this way. Okay, instead of hydrogen ion, we write simply proton. Okay, anyway, from the definition of a pH, the definition of pH is what? Negative logarithm of proton concentration. In this case, since this one completely dissociates, the proton concentration is same as this original, this former concentration, which is 0.1 molar. Okay, using the definition of pH, we get the the solution pH of this solution to be 1.00. All right, but uh, actually it is more accurate to use um, activity than this molar concentration. Okay, from here we calculate the ionic strength of the solution. Okay, and then it is 0.10 molar. Okay, the unit is the same as molarity. Okay, and from the table or using Debye-Hückel theory, you can calculate or you can obtain this activity coefficient, okay, of a proton. Okay, and instead of using molar concentration, you use this activity. Okay, using activity, however, you get different value for pH, which is 1.08. Well, this value is not much different from uh, this one. Okay, so that's why people usually ignore the activity coefficients. Okay, simply they assume that molarity is the same as the activity. Okay, okay, look at this one, these values. The, these compounds, HCl, HBr, HI, HNO3, they are all considered classified as strong acid. But actually, what are equilibrium constant or dissociation constant for these strong acid? Is it infinite? No, not infinite, but it has very large numbers. Okay, for example, this hydrochloric acid, this dissociation constant is about 10,000. For HBr, is about let's say less than 100, maybe 100,000. Oh no, 1 million, just less than the 1 million. For HI, yeah, it is very big, very large. It has a very large value. But problem is nitric acid. Okay, is dissociation constant is not small, comparing to the weak acid. This value is very large, but not very large. Okay, relatively small compared to other strong acid. Okay, so that's why you need to be careful when you are dealing with nitric acid, especially when its concentration is very high. Okay? So this next slide uh, shows the how well this nitric acid dissociates, okay, when its concentration is very high. Okay, the answer is that concentrated nitric acid is only slightly dissociated, not completely. Okay, dissociation decreases as the concentration increases. This is a general fact. Okay, this is a general fact, but the effect is more serious for this nitric acid. Okay, let's look at this figure. Okay? How do you know how much nitric acid dissociates into protons and nitrate ions? Okay, one way uh, to know is to use the Raman spectroscopy. Okay, you may not be familiar with Raman spectroscopy, but Raman spectroscopy is very similar to infrared spectroscopy. Okay, they gives the same information, the vibrational spectrum of the species. Okay, although the principles are completely different. Okay, at any rate, okay, let's take a look at these Raman spectra, okay, of nitric acid as a function of concentration of nitric acid, especially when it is very highly concentrated. Okay, as a reference, someone took the Raman spectrum of sodium nitrate. Okay, it has, several different peaks, 1, 2, 3, 4, 5, 6, 7, at least 7 peaks. Okay, but those peaks with this asterisk, yeah? Those peaks belong to undissociated nitric acid, and the one peak at at wave number of 1049. Okay, only this peak belongs to nitrate ion. Okay, so by comparing the peak intensity, especially this one and other peaks, you may know the how much this nitric acid is dissociated in water. Okay, okay, let's look at that. For 10 molar nitric acid, this concentration is already very high. Okay, there are not much case that in such a high concentration you work. Okay, but anyway, let's consider this high concentrations. Okay, for 10 molar nitric acid, this one, this peak is very prominent. That means there are uh, the dissociation is great. Yeah? But as the nitric acid concentration increases, okay, this peak belonging to nitrate ion decreases, okay, decreases, okay, and then another peak at this wavelength, okay, increases. This peak belongs to nitric acid, okay, and at the concentration of 23.4 molar, then this nitrate ion peak almost disappears, okay, and this peak becomes highest, okay, and this figure shows the fraction of dissociation. Yeah, this is y-axis. Yeah. When fully dissociated, the fraction uh, is 1, and it is 1, very close to 1 when the formal concentration of nitric acid is very low. Okay, and then it what it becomes going down, okay, going down, and almost zero. Then for the concentration greater than 20 molar. Okay, yeah. This is very peculiar for nitric acid, and at very high concentration. Why? Dissociation is very slight because there is no enough solvent to stabilize the free ions. Okay, at this high concentration. Yeah, that's why. And also, this table shows the temperature dependence of dissociation constant of nitric acid. All right. But contrary to our expectation, as temperature increases, the dissociation constant decreases. Yeah? We may think that at higher temperature, whoa, the dissociation may be greater than at the at the low temperature, but actually, the exactly the opposite. Okay. Well, and then our let's go to this part. Strong acid and bases, okay, since they are completely dissociates, okay, so we can calculate the pH of 0.1 molar KOH, okay, from the definition of Kw. Proton concentration is calculated by using this equation, all right, and then it is 1.0 times 10 to minus 13, and the pH is 13.00, okay, or you can directly calculate pOH, okay, which is defined as minus the negative logarithm of hydroxide ion concentration, okay, but people usually use not pOH but pH, so it is convenient to express our answer, you know, in terms of pH. But from the definition of Kw, pH plus pOH is all the time 14.00, which is pKw, all right, at 25 degrees C, all right. This is very important, and this is very easy to understand. Here is the dilemma. What is the pH of 10 to minus 8 molar concentration of KOH? Okay, you know, blind application of this calculation. You may calculate proton concentration equals Kw divided by this hydroxide ion concentration, and then you end up getting 1.0 times 10 to minus 6 molar, you know, for proton, and pH is 6.00. Wow, wow, it's absurd. You see, the KOH solution makes, you know, the whole solution acidic is absurd. It is impossible. Okay, how can the base KOH produce an acidic solution less than 7? It's impossible, and then we have to identify what is wrong. Okay, the answer is that we ignored autoprotolysis of water. Okay, but under the special case, you have to consider the water auto-dissociation or autoprotolysis. Okay, this one, since Kw is very small. It is 10 to minus 14, but in usual cases we can simply ignore water proteolysis, but the special case, like in this case, you we cannot ignore the water dissociation, and then we have to apply the systematic approach, yeah, to solve this one. Okay, so for this one we apply charge balance equation and mass balance equation. Okay, from charge balance equation we can write this one. Okay, the sum of participle charges is the sum of negative charges. Only there is only one negative charge, the hydroxide ion, but two participle charges. Okay, potassium and protons. And also we apply mass balance equation. Since this one is completely dissociates, mass balance equation is very simple. The potassium ion concentration is 10 to minus 8 molar. Okay, and then this is a default. Let me see how many unknowns: potassium, proton, and hydroxide. Okay, three unknowns. And how many equations? One, two, three. So it can be uh, solved. Okay, so let's solve. So hydroxide ion concentration, okay, is given by this one, and then potassium ion concentration is already known, and we put the proton concentration as x. Okay, so after rearranging these equations, then we get this quadratic equation. Okay, quadratic equation, and then very easily we can solve this quadratic equation, and we get two answers, but one answer is wrong, because it gives a negative concentration, which is impossible. So we take only one. So x, the proton concentration, is 9.6 times 10 to minus 8 molar. Okay, and the pH using this equation is 7.02. Okay, now after considering water dissociation, now pH becomes slightly more than 7. Okay, never becomes acidic. Okay, it approaches 7. So this figure shows that. Okay? This is a strong acid and strong base. Okay, and in the case of strong acid, when you dilute strong acid more and more, and then the pH increases, but never goes beyond pH 7. It approaches pH 7. Okay. Likewise, strong base, when you dilute the concentration, and then the pH decreases, and then it approaches 7. Never go below this 7. Okay. Yeah. So our dilemma is easily solved. Okay, very good. Yeah.